Welcome to the second last session of PyCon. We have Janal Javeri talking about scaling web apps. So take it away.
Thanks for the introduction. Yeah, I was just telling him it's Janal Javeri and how people get it wrong. The best one I've seen is Hinal Javeri. I live in California, so it's pretty close. Okay, so I'm going to talk about how we scale our Python web apps. By web apps, I'll be focusing more on social games because we are a social gaming company. So how many of you know what this slide is about, or how many of you have played any one of these social games? Okay, how many of you are on Facebook? Okay. So you'll be shocked to know that out of like 350 million people on Facebook, 70% of them actually play one of these games, or a few others. I mean, there are like 500,000 games out there. That's huge. That's a lot of people. So my talk is going to be focused more on, because we develop social games, and we are like a 95% Python shop. I would say almost 99%. We just have one Erlang message queue, but everything else is Python. So I'll be focusing on why it's tough to scale these games. This is the agenda for my talk. Why is performance a big issue for social games? I'll just go in like a high-level architecture of the talk, architecture of like social games, like how to actually work and what are the modules that we use, what are the main bottlenecks for social games, and then how we fix them. Some of the lessons we learned, I'll just share some of the performance strategies that we learned, and finally I'll open up for questions. So why is performance a big issue for social games? So what you see here is, at the top, you see a graph of one of our games. It's Dante's Inferno. Some of you might have seen the console version of it. It's by Electronic Arts. So we created a Facebook game with them. What you see is how many users we added in 6 days. We added 1 million users. That's huge. That's real huge. And just to compare how huge it is, the graph at the bottom you see is how much time it took Twitter to get to 1 million users. 9 months. So you can imagine how fast users get added to these social games. Why does that happen? These games are inherently viral. What that means is, if you log into Facebook, you see someone has attacked someone else, and your friend has attacked someone else. You see lots of quizzes, like what Sex and the City character you are, type of stuff. Those are all social games. They're super viral. You get lots of notifications. You get lots of emails, feeds from your friends. Some people consider it spam, but they are inherently viral. And the amount of time people spend, combined with they being viral, make them a really, really interesting performance challenge. So now we know why it's a big issue. Let's look at the high-level architecture of how these games work. This represents more of the modules or the components that we have, but it kind of represents, in general, like what social games look like. So when you're on Facebook, when you first type any apps, like let's say apps.facebook.com/band of heroes or Mafia War or thing, the first request normally goes to Facebook. Facebook proxies that request to your load balancer. You need to give your URL and stuff, but first request goes to Facebook. Facebook proxies it to your load balancer. We use HA proxy as a load balancer. Load balancer, in turn, sends the request to the web server. So we are a Python shop. We use pylons for most of our work. We use a pylons-based paste web server. It's a pretty simple web server. So the load balancer sends the request to paste. Paste, in turn, sends the request to your web application. Mostly, in this case, it sends it to the controller. Controller gets the data that it needs from the model, renders the template, gets the results, sends it back to the load balancer sends it back to the Facebook, and Facebook sends it back to the user's client. That's the very first request. Now, because we use an iframe-based model, all the subsequent requests go from the user's browser directly to our load balancer. As you see, we are a Pylon shop. We use Pylon, SQL Alchemy as our ORM. We use Mako as our templating language. Some other interesting stuff. We have, as I said, we have like 1 or 2% of our code in non-Python. That's one of the components. We use an Erlang-based message queue. That's something we wrote over one of the weekends, and it just works for us right now, so we haven't touched it. And then we have message queue readers, and so we do a lot of asynchronous stuff. I'll go in detail of that. We use memcached. We use MySQL as our database. Okay, so now we know like what a high-level architecture looks like. Let's look at like what are the main bottlenecks in this. So the first bottleneck is the load balancer itself. Like you want to make sure that as soon as you get the request, you want to send it to one of the web servers like as fast as possible. We use HA proxy as our load balancer. So we used to use Nginx, and we experimented with HA proxy, and we were like completely shocked to see that it just brought down the server load, like the load on our web servers. We think it might have to do with how HA proxy does TCP teardown. It just works for us, and it's doing a great job. We use round robin in most cases. There are a few cases where we need to redirect requests to only a few servers. In that case, we use like an IP-based or regex-based load balancing. The good thing about HA proxy is it's a very simple thing. It's a load balancer, and that's what it does. It does not care about like, gzipping a request. It does not know how to store static files. It's just load balance. That's what it does, and it does it really, really well. So now we have a load balancer, like a super sexy load balancer. What's our next bottleneck? Our next bottleneck is the web server itself. Your request came from load balancer to the web server. The job of web server is to make sure that it sends that request as soon as possible to the application layer. So we use, as I said in the beginning, we use Paster. It's basically something that comes by default with pylons. It's a very simple web server, doesn't do anything fancy. We have trimmed it down for our needs. We run like n instances per web server, where n is the number of CPUs. We start with 10 threads. And then, as I said, when I said we have trimmed it down for our needs, some of the things that we have done are like make sure that the request never runs for more than X seconds. We set it to 10. If it does, then we kill the request, log it. Email goes to engineer like, hey, what's going on? We also disable Nagel's optimization or Nagel's algorithm. I don't know if some of you know about this, but it's one of those things that were done in late 90s in TCP, where to avoid congestion, or basically to provide TCP congestion control, what they did was in the TCP layer, they wait for few more packets, or basically they wait for packets to batch up before sending the response back to the client. Now that works pretty well in some settings, but for us, we're like a social game. We want everything to be real time. And we noticed that this was actually adding 200 milliseconds of latency just to do that. We disabled it. There are a lot of discussions about like how Nagel's does not fit in today's world, but you can look it up. But yeah, that worked pretty well for us. So now we have a load balancer that's super sexy. We have a web server that's like pretty cool. What's our next bottleneck? It's the web application itself. We are a data-intensive shop, so we want to make sure that everything that runs, we want to make sure that we can serve the response back to the client as soon as possible, as fast as possible. So we try to cache everything, to the height of which we actually have integrated our ORM, SQL Alchemy, with Memcache. Here's the code that I think we got it from one of the news groups. It's a pretty simple code. What it does is, so the idea is that whenever we do a .get on any object, first it looks up in the session itself, SQL Alchemy session, and see if it's available in its identity map. If it's not there, then we do a get on Memcache and see if that object is available in Memcache. Only if it's not there, then we go to the next level where we actually query the DB. We believe that DB fetches are expensive. So as soon as we get it back from the DB, we again put it in the Memcache, and from next time onwards, it's available in Memcache. We do a lot of other optimizations for our Memcache fetches. We compress the response before sending into Memcache. we do one more interesting thing, which is probably it applies to the gaming domain, where a lot of time we need to find out if your Facebook friends are also our game users. I mean, as you can imagine, if you have like few million users and like 350 million users on Facebook, a lot of time you do not have friends playing the same game. But those finds are pretty expensive. So when we do it when we look for, hey, I mean, is this friend available? We send a request to the DB. That's more expensive. So we cache the fact that an object does not exist. We do it for a few objects. That helps us a lot because then every time we want to look up where people have common friends, we don't need to send a request to the DB saying, hey, is this user ID available in the DB? We also do, we have a notion of lists cache, which means that a lot of time, you must have noticed that when you need an object, you don't need the single object, but you need the list of all the objects all together. That's like to display a list of things. So we have a notion of list cache. So instead of just caching one object, we cache the whole list together. Even going one step forward, we have this notion of best effort caching. It's pretty interesting. So the example of that is, let's say you are in the game and you want to see like how many of your friends are online. So the way it works in Facebook games world is you query Facebook asking, hey, is the person online or not? Now, that's a pretty cool thing to look at, but then it adds a huge latency. So what we do is we ask the cache that, hey, cache, do you have this information? Only if that information is in the cache, we display it. Otherwise, we change the UI a little bit. We say that, we change the UI. We don't display the number of how many friends are online. So as you can imagine, you have to weigh between like functionality versus user experience, and we make sure that it's better user experience, it's fast. We do a few other things. We have this notion of local cache. A lot of time you have objects that are common to application that don't change that often. We actually cache them locally, like in the app itself. We don't even want to call memcache for that. We also applied a lot of Python speed performance tips that we got from wiki.python.org. Really cool tips if someone has not looked at it. Very simple ones, but they do give a huge performance boost. One of my favorite ones is xrange. I experimented and xrange versus range. So xrange I experimented and noticed that most of the cases is at least twice as fast as range. We do a lot of asynchronous calls. We make sure that anything that's not needed in the response, we make sure that that type of call does not happen in that request. We try to make it asynchronous. Calls to Facebook, calls to log processors, calls to event tracking for analytics and stuff, everything is asynchronous. And we do it using the message queue. The request puts it in message queue, we have message queue readers that read it, do the work. We also do a lot of, we also make sure that we only return the stuff that's needed or that has just changed. We don't return anything else, so we do a lot of partial rendering, Ajax stuff, reading JSON, and all that stuff. Now we have a super cool web application. Our next bottleneck is browser itself. Like once you send the data to the browser, it still takes time to actually render that data. If you were told to just do one single optimization, I would suggest try gzipping a response. Here is the graph that you see. As you see on the start of Vic-Fi, you see a huge drop. That's because of gzip of response. That's a huge, and actually it was kind of alarming. Some of our sysadmins were shocked, like, hey, what happened to our outbound traffic? Some people complain that it actually increases the amount of CPU used on the servers. That's a valid concern. We experimented with different compression levels. In gzip, we settled with compression level 1. And as you can see, the graph below, it displays our CPU usage, and you see it was hardly any effect on the CPU. It just did well. We do a few other optimizations, like we use CDNs. We do this 1-second trick where some of you might know that when you load an image from a domain, it's blocking. So So when you're loading an image from a domain, you can't load a second image in parallel. So we kind of cheat, and we have like a pseudo names for our host, aliases for our host. And what we do is we put those pseudo hosts in our HTML code. So browser thinks that those requests are two different hosts or two different domains, and it tries to do it in parallel. We do a lot of ajaxification, as I said. We do a lot of client-side caching. Make sure we set appropriate cache control headers and stuff. Okay, so we saw load balancer, we saw the web server, web application, browser. What did we learn from this? So I'll share some of the performance strategies that we learned. One single most important thing is measure, like measure the load balancer request time, the web server request time, the controller request time, how much time it takes in rendering. We use a very simple middleware. It's based on the time. You just import time and time.time. It's by the way, I forgot to mention, it's WSGI, so it's very easy to integrate it as a middleware in your web app. This is how this is what the time middleware is like spits out. As you see, it's basically showing how much time each request took. What we do is we graph it. This is super useful because whenever we make any change in the code, we push it out. Immediately, we go to this graph and make sure that we haven't affected latencies. I mean, this sounds extremely simple. It's done using cacti, but it's super, super useful. We also use some of the fancy profilers. We use one called Repos. I think it's part of Repos BSG. We have integrated with our WSGI app. It's probably based on cProfile because the output is very simple, very similar to cProfile. Some of you who have used it kind of know what's going on here. For some of you haven't used it, I'll just go in like a brief detail of what it displays. It displays, so this is important, like this shows what line of code, where, what it's talking about, and then the first column is the number of calls that happen to that. Second is total time it took to run those calls, just those calls, but not the sub-functions. Cumulative time is it took to run those calls as well as the sub-functions. That's the one I look at most because I kind of know, hey, and this is the main bottleneck. Of course, you also want to keep an eye on the number of calls. You might find out, hey, I mean, I don't need to call this function so many times. We also do a lot of memory profiling. We use Dozer for that. We had an interesting case where we saw a lot of our servers are leaking memory, like they'll just go like use 8, 10 gigs of memory. We started using Dozer. Immediately it told us that we had this crazy amounts of routing objects, and we were like, what's going on there? And we figured it was something that comes in pylons where the route cache was enabled. What it does is for every URL, it remembers what controller it's supposed to hit. Now that works pretty well if you don't have that many URLs. For us, the URLs have user IDs in them. So for every user, we were actually caching that fact. The change was like one line change, we disabled the routing cache, it just worked. Because we are a data-intensive app, we do get into a lot of database issues. I won't go in detail of all of them, but one of the interesting ones we see is, so we have this thing where, let's say you and your friend are playing and you are attacking one of the characters in the game. What you're trying to do is change properties of, in a layman's term or in a CS term, trying to change properties, or you're updating a row in the database. It works pretty well if you don't have that many users, but when you have millions of users, you can end up stampeding or overwriting each other's change. What SQL Alchemy does or allows you to do is give like a version ID to that thing. So as you see in this case, process 1 and process 2 are updating this data. The version in the database is version 16. If process 1 ends up updating it, the version becomes 17. So when process 2 tries to update it, it knows that, hey, someone else has changed it before I could do it. Okay, I'm going to run a little bit fast. So the last thing I'm going to talk about is an experiment we did using Tornado in our production setting. It was super easy to integrate because we were WSGI. Tornado is probably not meant to be used directly with WSGI because it just destroys the main purpose. But all our apps were written in WSGI, so we tried it out. The graph that you see is, on the x-axis you see is the type of request, and on the y-axis what you see is by what percent Tornado does better than Paster or existing web server. Here is what we noticed. As I said, we used it over WSGI, so it's not exactly leveraging its capabilities. But what we noticed is CPU and memory usage went down by from 5 to 10%. What we were shocked to see is that it did not do well for responses with a higher size. So we did not end up using it at production setting for that app. But we also noticed that it was really good for small size requests. So we plan to use it for our asynchronous and real-time needs. I'd like to thank the whole Law Labs team and my lovely wife and my 11-day-old daughter, Gia. And questions? Sure. Yeah. Oh, yeah, I'm sorry. The request was to go back to the database slide and finish that up. Yes, I realized I skipped how we trace database connection leaks in SQL Alchemy. So SQL Alchemy, how many of you use SQL Alchemy? Okay. Probably you already know this, but the most easiest thing but most useful thing I find is using echo. As soon as you set echo equal to true, you know what type of crazy queries you're sending to the DB. If you want to go one step further, you can set echo underscore pool or set the logger accordingly, and you know when the connection is taken out from the pool, going back to the pool, and a lot of internal stuff. I find it really, really interesting. The other thing I want to talk about is, so one of the biggest fixes that completely helped us is a lot of time we used to have these transactions that won't finish because of some problem. The best thing we could do was set in the finally of the base request for pylons, we would roll back all the transaction. So we don't care what happened to them. We'll just roll back and remove that transaction. And that fixed a lot of our transaction connection leak issues. Does that answer your question?
Thanks.
Okay.
With the locking stuff, with the versioning, where you have two processes, what's going on?
Yes, so that's optimistic versus pessimistic locking. The idea is, so if you have a row in the DB and two processes are going to update it, one thing you can do is have a lock on it. The other thing you can do is assume that that's not going to happen that often. So instead of locking, you have a version ID for every row. And whenever that update happens, that version gets changed, get updated. Which means that if you have two processes that think that the version of, for example, in this case, the data is 16, if the first process changes its version to 17, and in the meantime, if process 2 comes and tries to update it, it knows that, hey, someone else changed it before I could do it. So then SQL Alchemy is pretty smart. It throws concurrent modification error, and then we let the application replay the whole action using the new data.
So it will go off and refetch the new
Yes.
What do you use for application logging?
Locking?
Logging.
Oh, logging. We just use standard loggers, but are you asking more in a sense of distributed logging, or we have standard loggers that just write to the local file, and then we have log pushers that push the logs to a standard server, and then we do all the processing.
So is your application sort of internal between your servers? Is there a lot of intercommunication internally, web requests between your servers, or is it all external stuff?
There are a few internal requests. It's a good question. Yeah, there are a few apps which talk to each other to get some of the data. For example, if you are on one app and we want to display if you have any users in the other apps that we have or in the other games, then they kind of do talk to each other. But I won't say that much at the web level, not a whole lot. Our ad module, our ad app, it's like a pylons app which is used by all the other apps, so we do that.
So we have a very restful system. It's actually 15 services talking to each other, and we find that a lot of fine-grained RESTful requests between the servers is creating a lot of latency, and wondering if you ever have to pipeline any requests between your servers.
We haven't done that, yeah. I'm sorry.
Just wondering which Erlang message queue you use?
No, so, okay, this is an interesting question. We have an Erlang-based message queue, but we wrote it. It was something that our CTO, Brian Rue, wrote over like one of the weekends. Okay. It just works, yeah, so we didn't care about it, yeah. Any other question? Okay, thank you.